Today we are going to be talking about IR spectroscopy, a rapid, inexpensive and a non-destructive method, which is one of the most common spectroscopy techniques. It can be used to characterize new materials or identify and verify known and unknown samples, which makes it an important tool in the lab. In this video we are going to focus on the most important parts of FTIR, so you would be able to use this technique and analyze the acquired data. As we know, molecules are not stationary. They are always moving around, and for example, the single sigma bonds are also freely rotating. One type of movement the bonds can also have are molecular vibrations. Molecular vibrations can be the following: symmetrical stretching, asymmetrical stretching, scissoring or bending, rocking, wagging, and twisting. But in this video, we're mainly focused on the stretching vibrations. We can think of these stretching vibrations as oscillating springs. Let's take a look at the carbon atom connected to a hydrogen atom by a spring. From physics we know Hooke's law, and the spring constant K can be thought of as the strength of this bond on a simplified level. When the atom absorbs IR light, it gets excited into a higher vibrational energy level, where the frequency of oscillation stays the same, but the amplitude of oscillation increases. The frequency of this oscillation can be derived, and the formula is the following, where the frequency depends on the mass and bond strength. Let's take a look at two carbon atoms connected by a single bond. Here, instead of normal mass, we use reduced mass. If the bond again absorbs IR light, it gets excited to a higher energy level with a certain frequency. If we replace the carbon atom by the hydrogen atom, the bond strength stays pretty much the same, but the reduced mass gets a lot lower. If we look at the formula, then we see that the frequency gets higher. Now let's look at two carbon atoms connected by a double bond. We see that the reduced mass is the same with the first situation, but the bond is stronger, causing a higher oscillation frequency again. If we now take a look at the IR spectra, we see that on the x-axis is the wave number with the unit of reciprocal centimeters. This is just 1 over the wavelength absorbed. When calculating this, it is important to take into account the unit of centimeters to not make any mistakes during calculations. If we now take the frequency formula and make it show the wave number, we get the following. The same applies that the wave number is proportional to the square root of the bond constant and inversely proportional to the square root of reduced mass. Let's now take a look at the IR spectra of 1-hexene. On the x-axis we have the wave number, and on the y-axis we have transmittance, so the percent of light that reached the detector. We can divide the spectra into two halves, the fingerprint region and the diagnostic region. The fingerprint region is unique to each molecule but is quite complex and is out of scope for this video, so we focus on the diagnostic region, where there are mainly stretching vibrations of typical bonds. Here we see a few very specific peaks. Let's start with the highest wave number, so the peak around 3300. This is the CH stretch, so the one shown on the slide. Then we have the other hydrogens at a peak around 3000. So why are they different peaks? This happens due to the reason that the sp carbon has more of the s orbital characteristic than the sp3 carbon, making the bond between the sp carbon and hydrogen stronger and appear at a higher wave number. This is due to the reason that the bond strength constant is higher and the frequency of oscillation is thus also higher. Finally, we see the triple bond around 2000 reciprocal centimeters. This bond is stronger than the carbon-hydrogen bond, but the reduced mass is again significantly higher, leading to a lower wave number. If we now replace the triple bond with a double bond, we see the peaks moving. This time we have a sp2 carbon connected to hydrogens, appearing around 3100, and the sp3 carbon hydrogen around 2900. This is again due to the same reason as before. The double bond is also at a lower wavelength, as the bond is weaker than the triple bond. In reality, we use a table to match the peak to a corresponding functional group. The peak intensity is also noted down, which aims to make the identification easier, as with some bigger molecules the spectra can look much more complicated. Also keep in mind, only bonds that create the dipole moment are IR active. Let's now have a look at the IR spectrometer. It can be of various sizes, but most of the time it looks something like this. The instrument has different ways of measuring samples, dependent on the properties of the sample. We will be looking at transmission and ATR, or attenuated total reflectance. Transmission is used to measure liquids, gases, and films, where the IR light passes through the sample, and ATR is used to measure liquids and solids, where the IR beam is reflected off the sample using a crystal. This allows us to measure strongly absorbing materials. Let's start by looking at ATR. On the top is the place for the sample, together with the sample presser. When operating the machine, turn it on from the bottom by pressing the green button. Make sure that the orange light also turns on, as this indicates a dry environment in the machine. Then, turn on the computer connected to the machine and open Lab Solutions IR, and from there move on to the spectrum feature. The machine will then initialize. If you encounter any errors, make sure to recalibrate the mirrors. On the right, you can adjust the settings of the measurement. Keep in mind, using a higher resolution, it also takes longer to measure. Usually leaving it on the default settings works fine. If you are ready, then start the background scan using the button PKG Scan. To know if everything has been performed correctly, then the resulting graph should have the same shape as seen here. To measure a solid sample, place the sample on the correct spot and press it down using the red knob. In our case, we are using DCC or dicyclohexyl carbodiimide. The machine will automatically detect the correct pressure, so do not worry about over-tightening. Be careful when adjusting the metal tip height, as this can break the machine when too tight. Go back to the software and select correct folder destination for your files to be saved to. Then press Sample Scan and wait for the results. The resulting IR spectra will be displayed. Make sure to clean the sample holder with a corresponding solvent and also clean the metal tip. The tips can also be interchanged to better suit the measured material. To measure a volatile liquid, use the attachment provided. Assemble the setup as follows, and you might have to adjust the metal tip height, as the setup is higher than the usual sample. Then add your volatile liquid and close it. Then clamp down the machine and take the measurement. The graph will be displayed on screen. When you obtain your results, first do a baseline correction. This can be done automatically or manually. By pressing Calculate, the baseline is adjusted and we can move on to the peak pick screen. First, adjust your threshold and noise level on the top right. Picking a noise level around 5 will work fine. To add peaks manually, press Add Peak and then click on the spot where you want to add the peak. Press OK and go to save your file. Press File on top left and then Save. If you want to export the file, open File, then Export. This will result in a text file, which can be then opened in Origin. If your sample is in a solvent, then you have to use another attachment. Remove the ATR unit and be careful not to break the ridge on the bottom of the ATR unit. Then attach the sample holder using the screw, where you can add your sample later on. First, we need to do a baseline correction with just the solvent. We will be using dichloromethane. Add the sample and do a background scan again. The graph follows a similar shape, but some parts now have a transmission of 0, meaning these parts cannot be analyzed later on. Make sure to use an appropriate solvent for your sample. Then add your sample and solvent to the sample holder, close the lid and take the measurement. This time there is a lot more noise, but we still see a peak. Mark it manually and adjust the scale to visualize the peak better. Let's now take a look at the obtained spectra. We can spot the peaks around 2900. These are the CH stretches. And around 2100. We see the characteristic cyanamide peak. This is how we can identify this compound. For DCC in dichloromethane, or DCM, it is much harder to see, but there is a peak around 2100. We measured the solid DCC before, and if we compare the two, we see that the cyanamide peak is still there. The common applications for FTIR are tracking of reaction progress. On this graph we can see the IR spectra taken at different times, and we can see how at the start there are almost no peaks, but they start to appear. By doing this, the reaction progress can be tracked. FTIR is also used in the food and beverage industry, where it can be used to see if the food is in correspondence with the label. It is also used in the medicine and chemical industry to identify which functional groups are in the produced compounds. Always contact the lab supervisor when having issues using the instrument. Thank you for watching and good luck in the lab.